Hi, everyone. Thank you for the introduction. My name is Leiting Sang. I'm a research scientist at Waymo. I'm very happy to participate in this workshop to share some findings about machine learning models for autonomous driving. So as you can see on the title, today I'm going to talk about the recent work that we have done on the evaluation of the robustness of motion forecasting models. First thing first, what this work is about. As you might know, more and more deep learning models are deployed in more safety-critical applications, such as behavior prediction and motion planning in autonomous vehicles. So since those models are safety-critical, we'd like to evaluate how those models, particularly for the models used in behaviors, can be generalized across different scenarios. So we actually trying to answer two questions. The first one is, what are the generalization failures? And the second one is, are they really happening to the state-of-art motion prediction models? If so, how could we evaluate them? Before I dive into the details of this work, let me first give you a very brief introduction of the motion prediction models. So typically in the motion prediction model, we have some input. It's what we call X, which includes some historical trajectories of the ego agent and that of the contact agents. Of course, we also have some information about the road graph or traffic light, all sorts of surrounding informations. As for output Y, we are trying to predict a distribution of the future trajectories of the ego agent. So what we are trying to learn is actually a mapping function from the input X to the output Y. So with that, you might ask, why do we even care about the robustness of the prediction models? So here, I'm going to use an example to demonstrate the purpose of this work. On the left side, we are using a very recent model called semi-transformer model. This is a prediction result on one single data. As you can see, the blue one is the ego agent. The green ones are the contact surrounding agents. This is a pretty good prediction because as you can see, all the blue trajectories, the predicted blue trajectories are very reasonable. And one of them is actually very similar to the ground truth, which is the gray dotted line. What we have done is actually we added a small perturbation to this data, and we are trying to evaluate how the new prediction on the perturbed data is going to behave. So on the right side, I'm showing the new result. The perturbation we have done is we remove those two surrounding green agents because they are traveling on the opposite lane for human driver because they are relatively far away from the ego agent and they are traveling on the opposite lane. So we believe those two agents is not significantly impacting the behavior of the ego agent. But you can see using the same model, however, the new prediction is actually generating a misdetection of the ground truth. So this is why we think this is very critical, because if we are missing the ground truth mode, there might be some collision happens if we just do motion planning based on this prediction results. So the next question will be like, how does the generalization failures come about? Let me try to explain this in theory using a very simple example. So as you can see, typically for machine learning model, we have some positive or negative data. This is just a very simple classification problem. We are trying to fit a model. For example, we found a model. We believe this might be the right model until we have out of distribution events. So when we are trying to evaluate the robustness of machine learning models, we're actually trying to evaluate the model's performance on inputs that are very similar or realistic to us, but might be out of distribution of our collected training data or test data. This is very important for safety critical systems. So in order to do that, what we are proposing is what we call perturbation analysis. Imagine this circle is the whole input space that we want to evaluate our motion prediction models or like motion planning models. And unfortunately, we can only collect very limited training data. For example, that's in the purple circle. As for the evaluation data or testing data, we might be able to collect more data, but it's never possible to cover the whole input space. So there are still lots of scenarios in the whole input space that we still want to evaluate a model. So how can we do that? An effective tool might be, okay, I know that we cannot collect all data, but it might be possible that we can add in some perturbation to the existing data and generate some auto distribution, but still realistic testing data. So, but in order to do that, there is still a challenge, which is how can we efficiently generate realistic perturbations that do not alter the ground truth of the ego agent? Because if we alter the ground truth of the ego agents, then we can no longer evaluate the robustness because we don't have the ground truth for the prediction models. So in this work, we actually focus more on the robustness of the models, trying to pick up the interaction among agents while maintaining the ground truth of the ego agents. So to do that, the concept that we are proposing is we are trying to construct some causal agent by human labelers. So for causal agent, our definition is that for any agents whose presence would modify or influence the human driver behavior in any way. So if an agent is impacting the ego agents, then we are calling that as a causal agent. Since causal agent is inherently a very subjective concept, so we do ask multiple human labels to label the causality of the agents. Let me give you a simple example. So for example, in this scenario, we're asking the labelers to check on the video and label out all the causal agent that he or she believes that agent's behavior is going to impact the ego driver. So for example, in this scenario, we believe the agents in the green circle are causal agents, but the agents in, for example, those two red circles are non-causal agents. So with that, we actually labeled all 14 4K examples in the Waymo open motion dataset, validation dataset. And we did some statistical analysis of the labels. We found some very interesting conclusions. First of all, we found that in each scene, not so many agents are causal. In most of these examples, only about 14% of the agents are causal. The second observation we found that is the causality of the agents is closely related to the distance from the autonomous vehicle. Most of the causal agents are closer to the ego agents. The third observation, we found that we checked the likelihood of the agents being causal in each different type. It turns out that a cyclist is most likely to be causal. That might be because that cyclist is sharing the road with the autonomous vehicle and closer to us in general. But vehicles might be far away and pedestrians might be on the road curbs. We do release all the causal labels and perturbations, and you can download all the causal labels and perturbations at this website. With all those labels, we have created 4 different perturbations. The first one is removing causal. This is just being acting as a sanity check. The second one is removing non-causal. This is the most important perturbations because we desire our model to be robust under this perturbation. The third one is removing non-causal equal, which means we remove an equal number of non-causal agents as there are causal agents in the scenario. This is just like as a control version of experiments. The final one is removing static, which are removing agents whose XYZ position does not change during the historical period. This is just working as an additional perturbation. So with all those perturbations, we have evaluated on 3 different state-of-the-art models. The first one is multi-pass plus. The second one is syn-transformer model. And the final one is the waveformer model. You can find details about all the 3 models using the links below. We chose those 3 different models because they are using different architectures. For example, multi-pass plus are using LSTM, syn-transformer and waveformer are using transformers, but they are using different coordination systems. For the metric, we are using minimum ADE, which is the closest L2 distance between the predicted trajectories with the ground truth trajectory. With that, let me show you some performance of the models under different perturbations. The first results I'm going to show you is the removing causal perturbation for multi-pass plus. On the x-axis is the original minimum ADE, and the y-axis is the perturbed minimum ADE. The surprising results we find is that removing causal actually can sometimes leading to better minimum ADE. The next results I'm going to show you is that the performance of the model under removing non-causal, removing non-causal equal, and removing static. For a robust model, we expect all the points under remove non-causal perturbation to be on the diagonal line, or at least closer to the diagonal line. But however, you can see here, we're seeing lots of points which are actually off the diagonal line, meaning the model's performance is changing significantly under the perturbation. And here, same story. Even for removing non-causal equal, we're seeing there are lots of points which are significantly deviating from the diagonal line, even though it's much less than the removing non-causal. And comparing the results between the removing non-causal and removing non-causal equal, we can see that the model is actually more sensitive to the amount of the agents that we remove. If we remove more agents, the model is less robust. So here is a summarizing quantitative table for the robustness of different models. As you can see, across the 3 different models, we are seeing that the syn-transform model is acting more robust compared to multi-pass plus and the waveformer. We also sliced the robustness along important features. We chose 3 different features. The first one is the ratio of removed non-causal agents versus all the agents in the scenario. We can see that across the 3 models, syn-transform model is more robust along different ratios of removed non-causal agents. The middle one is we are slicing the results along the autonomous vehicle's speed. We're seeing that, again, the syn-transform model are more robust when the speed is less than 45 miles an hour. On the right side is the slicing results over the minimum distance of non-causal agents to the autonomous vehicle. And we can see that the waveform model is more robust when all the non-causal agents are relatively far away from the autonomous vehicle. This might be because that the waveform model is using ego agents coordination system, while the syn-transformer is using the global coordination system. We also have triaged some examples. Here I'm going to show you a few. The first example is a positive example with good robustness. As you can see, on the left side is the original scenario and the original prediction. And in the middle one is removing causal being, you can see actually those 4 agents are being removed. And you can see if we remove the front vehicle, we actually can generate a much faster prediction, which is very good, like causality performance. But on the right side if we're removing the non-causal agents, we can see the prediction can still maintain the same, almost same to the original prediction. So this is a very, very good example, or a very positive example with good robustness. And then let me show you some bad examples with like poor robustness. As you can see, again, on the left side is the original scenario. There is our eagle car is just traveling on the very straight road with a oncoming vehicle. And then with removing causal one, we are just removing the oncoming vehicle. As you can see, the prediction is actually maintained the same. This is good, but on the right side is we are removing the non-causal agents, we're removing the agents which are parked far away from the road in the parking slots. But you can see our prediction actually surprisingly slows down. This is not matching the human intuition. So we call this as like poor robustness. This is another example from scene transformer with poor robustness. This is also the motivating example I just showed you before. As you can see here, if we remove those two non-causal agents, we are actually generating a prediction without a critical mode, which is exactly what the ego agent actually doing in the ground truth. Here is another example. The ego agents is trying to go through an intersection, and we are removing some non-causal agents, which are still some agents parked on the side of the road or very far away from the intersection. As you can see, again, the new prediction on the perturbation data is generating some predictions, but missing to detect the ground truth. So what are the potential solutions? In this work, we do explore some potential solutions. We found that first, increasing the training data set will help. What we did is actually we using 10%, 10, 20, 15, 18, up to 100% of the training data. And we found that increasing the training size can not only increasing the original performance, but also can increase the robustness of the model. The second solution we have explored is that we have tried some data augmentation, and we found that data augmentation can help, but although it cannot help significantly. So now you might wonder where are those non-robustness might be coming from. During our triage, we do have summarized some patterns, and I would like to share with you. The first hypothesis is that we might be fitting to spurious correlations in the training data. By spurious correlation, I mean features that are correlating with 13 ground truth trajectory, but fail to generalize. For example, on the left side, I'm showing you the original prediction and the perturbative prediction of a model which are trained at 210K steps. So you can see the model is working pretty good because removing those non-causal agents, we are still maintaining the same prediction. On the right side, we're showing exactly the same data, but we purposely overtrained this model until 1 million steps. So with this significantly overfitting model, you can see under the same perturbation, the model is generating a surprisingly slow down prediction, which is very counterintuitive. The second hypothesis is because of distribution shifts. This is because we compare the performance of removing non-causal and removing non-causal equal, and we found that the larger the distribution shift is, and then the more sensitive the model is. So we believe distribution shift is a potential reason of the weak robustness of the models. The third hypothesis is that the model might be over-relying on agents instead of the road graph information to figure out where are the drivable zone or where the prediction might be. So we observe it because we actually observe examples where dropping non-causal agents create predictions that disobey the road graph rules. For example, here, under the perturbation, we're generating a new mode, which obviously is violating the traffic rule because it's going into the object lane. The first hypothesis is that there might be some data-dependent modes that are missing in our training data. That's because we observe many failure examples that are missing or generating new modes after the perturbation. And there might be more hypotheses, and we welcome the audience to explore our labels and find more hypotheses or reasons for the poor robustness. So as a summary, we have constructed a causal agent labels for the Waymo open motion dataset, and all labels and perturbations has been released at this website. So feel free to download and explore the usage of those labels. And second is we provided a benchmark for robustness evaluation of trajectory prediction models, leveraging the causal relationship among agents. We have found some surprising results. First, better prediction results does not equal to better robustness. And second, most of the public state-of-the-art models are not as robust as we expect them to be, especially when they are being deployed on autonomous vehicles. For future work, of course, we would like to deep dive into experiments for the causes of the robustness issues. And more importantly, we are trying to explore better solutions. For example, if the data size is the key, so we might explore performance with even larger data set. Can we design data augmentation to be more effective? Or can we design better network structures or better input representations that encourage robustness? That's all. Thank you very much. Any questions?